All right, welcome to part 2 of projections on the lines and subspaces. And I was nervous about the first part in the intro, so hopefully it works out because I think it's easy to kind of read in the textbook and follow what he says, but it also gets very, very technical, which is really hard to do in like a 10-minute video. And so hopefully it's helpful. If not, just disregard the part 1, and I would encourage you to take a look at the book. In this part of the video, what we're going to do is really describe how we are projecting a vector B onto a vector A that runs through the origin, and the calculations that take place into that, and then look at an example. And through that, hopefully make sense of, again, the part 1 video and ultimately what we get from this when we're trying to do this projection. So again, what we're trying to figure out is if I take my vector B, I want to know how much of B is in the direction of A. Again, what I like to think about, and this is true in forces and work and all that kind of stuff, is that if I was to cast a shadow directly onto A, so notice that orthogonality, so how it's perpendicular. If I was to cast a shadow, I want to know how much of B falls onto A. And so essentially what we're trying to figure out is I want to know what is this vector here. This is my vector P. This is the projection that we're trying to find. This was the lowercase p in the first video. How much of that vector B of 2, 3, 4 falls onto my z-axis, and that was 0, 0, 4. That was that projection. And then from this, because notice how this is in the same direction as A, if I can find the matrix for this, we're finding the column space then, because now any vector B that I want to draw would project onto this same line. We're essentially now finding a column space. We can use the column space to help us now for any single problem. And so our first step here is that we need to figure out what P is. And what I want you to notice from this is that P is equal to some scalar version of my vector A. Notice how it's going to follow in the same direction. It's just a scaled down version or a scaled up version. And so the name for that scalar that the book uses is x hat. So x hat is not a vector, it's a scalar. It's what's going to ultimately allow me to shrink A or enlarge A so that it matches the projection or the shadow that we want to find here. And so it's some scalar times A. And this creates my vector for my projection, right? It gives me the direction in that scalar piece. Now when I'm doing this, and it's going to be kind of weird because I use red for my projection, is this point that we're finding, this is the point that is closest to B on A. And so because of that, this shortest path right here, I'm going to call this E. And he refers to this as the error. In other words, if this vector represents the true solution, and we're getting something out to here, like this is how far off we are. It is the shortest distance, the least error that we have. And in the next section 4.3, you'll see something called least squares method. And if you've done statistics and if you've looked at regression, the least squares is the way to essentially plot data points and find the best line of fit. And you're essentially doing a least squares approach, so we're going to see this play a role later. But the takeaway for us right now is that this is always going to be forming a right angle, that E is orthogonal to the vector A. So because of that orthogonality, I know that E dot A has to be equal to 0. So we have this fact as well. And we're ultimately going to use this fact as well as seeing what E is equal to help us figure out what is x hat, because that's what we need to find. To find this projection, I need to know this scalar. Well, right now we don't have a way to find x hat, so we're just kind of looking at this essentially graphically, and we're going to use some facts about orthogonality to help us determine that x hat. So when I'm looking at this, notice that if I do P plus E, that gives me the vector B. So I'm going to swap here to my other marker. Again, if I'm just looking at this in terms of vector addition, notice that P plus my error is always going to give me that B vector. And so from here, what we have then is that E is equal to B minus P. Well, B again we know. A is given as well. And so now, based off of this information, we can use our orthogonality to set up this equation. A dot E, so A dot B minus P should always be equal to 0. B is a vector, P is a vector, where P is x hat A. So A dot B minus x hat A has to be equal to 0. And then now I can use my dot product properties to distribute the dot product. And so I'm going to get, I know this is going to be kind of low in the video, but A dot B minus x hat A dot A equals 0. And now we can solve this for x hat. And if I add this over and then divide by A dot A, we essentially get, going kind of right to left, apologies, is A dot B over A dot A. This gives me my scalar. A dot B is a number, A dot A is a number. This gives me my scalar for x hat. And now we have our projection vector P. It's the projection of my vector B onto A. But remember that dot products can be described by using inner products and transposes. And that's going to be really, really important because when we want to now think about projecting in terms of a matrix, we found our one answer for here, but if I want to change B, can we write a projection matrix that would do this all at once? Then this isn't really helpful because this only applies to vectors. And so by rewriting this as A transpose B and A transpose A, still yielding the same result for x hat, we can now then apply this to matrices and ultimately subspaces in the next video. But for now, here's our way to find x hat. Now, the fact that we have x hat, I have my projection vector, but now again the question is if I want to change B, the projection is still going to put me onto A, meaning that there is a column space here that would construct any projection that we want. We want to find the basis for that column space. We want to find a matrix to represent that. And so what we're going to actually use is this formula here for x hat A, where instead of thinking about it as resulting in a vector, I want to result into a matrix. And it's kind of a clever way of doing this, and if you follow along in the textbook, it's really easy to kind of see the work. I think this last step is the one where the work isn't as clear. That if I want to create a projection matrix P, if x hat is A transpose A over A transpose B over A transpose A, we just swap the order. In other words, if I was to put the A in the front, and then the A comes out, the B slides over, I now have this. A transpose is a matrix, A transpose A is a scalar, times or dot with B, that vector here. This will create our projection matrix for P. And in our scenario here, because B is a line, this will result in a rank 1 matrix that now can take any vector B and project it onto A. And it won't, so again, in other words, this found us our very specific, unique solution. This will allow us to find the projection matrix for any problem and any vector B that we want. And so again, notice how that's based off of just my vector for A. And now B can be anything we need it to be. So it all stems from essentially this, again, geometric, the orthogonal piece here, solving for x hat. We can find my projection of B onto A, and then from there we can find our projection matrix P. And here's where I'm going to go ahead and stop the video to keep things short, but I'm going to work the two examples from the textbook that goes with this idea so you can kind of see how all the numbers work with the formula.